Hello, welcome again to the second tutorial in GAMS. Today we have a tutorial in transshipment problem. Before continuing to solve the problem in GAMS, I would like to introduce what is transshipment problems. There are many applications of transshipment problem. For instance, in flight connections, the example of is that, for instance, if you uh, uh, a flight from Denmark to some other country in Middle East or United States, most of the time you will have a connection in a certain port, for instance in Singapore, in Thailand, or maybe in London to continue further into your final destinations. And again, another application of transshipment problem is vessel transshipment in international cargo vessel. Mostly one vessel will deliver to transit terminal, for example in Singapore, from Denmark to Singapore, and from Singapore continue to another destination, for instance in United States or in Australia or in India, depending on the itineraries uh, of the travel. And another application is multimodal transportations. For instance, if you would like to go from Sudhown train station to Bausfair, uh, oh, no, not to Bausfair. For instance, from Sudhown to other city, for example to Aarhus, you will stop at Copenhagen Central Station, and you change another train to Aarhus. Uh, that's an example train to train transshipment. And then we have also train to bus. For instance, you go from Hamburg to Sudhown. You will depart by train to Puttgarden, and Puttgarden you will deliver into ferry to Rodbu Farrer. From Rodbu, you will continue by train again and until Copenhagen Central Station. And from Copenhagen Central Station, you will continue the travel using mass rapid transport train to Sudhown train station. That's some examples of transshipment problem. Today we will have an example, but not that complicated as we have mentioned just now. But it is a simple training for you to be able to understand how to deal with transshipment problem and how to make model of transshipment problem and to code in GAMS. And the objective is that at future you should have be able to implement this knowledge of coding transshipment problem in GAMS into real application whenever you go for your future jobs. And yeah, now we will go further into our uh, test in transshipment problem. In this exercise, we have an example of delivering products from two suppliers, Nebraska and Colorado. Each of these suppliers has a capacity of 300 unit per day. And in order to deliver to final destination in Chicago, St. Louis, and Cincinnati, uh, they have to travel through transit point. Here we have three transit point: Kansas, Omaha, and Des Moines. Uh, the number here, for instance 16, 15, 10, represents the unit delivery cost. For instance, to deliver from Nebraska to Kansas, it takes 16 US dollar per unit of products. Or for instance, it is, if we assume that this is a travel, which means it is 16 US dollar per person. And The task of this exercise is that to find the optimal solution that can minimize the total cost of the networks. For instance, how we deliver products or persons or passengers from Nebraska to Colorado, uh, Nebraska and Colorado to Chicago, St. Louis, and Cincinnati by using by uh, going through some transshipment points in Kansas, Omaha, and Des Moines, because there is no way you can go directly from Nebraska to Chicago. You will have an opportunity to travel from Nebraska. You have to stop at Kansas and continue further to Chicago, or Nebraska to Omaha and then Chicago, or Nebraska to Des Moines and then to Chicago. So that's a problem. And now we are going to model this problem into GAMS. But before doing the modeling in GAMS, we should be able to formulate these problems into mathematical model. And therefore, I have composed the models. As you can see here, we have in this, as compared to assignment problems, here we have three in this. I for sources, J for transshipment points, and K for final destinations. And we have also given data. AI, it is a supply of commodities of source I, and BK, demand of commodities at market source K. We have two different costs here. For instance, here we have CIG. It is cost per unit shipment from supplier to transit point, and CJK. It is cost. Cost here is represent delivery cost per unit shipment from transit point J to K. Okay, I will add delivery costs. So it's very clear that it is not production costs or inventory cost. So it is exactly delivery cost. We don't consider here inventory or production. Of course, we could develop further the model, but at this point, just assume this is delivery cost. And there are two different types of decision variables. XIG, it is the amount of shipped commodity from I to J. Depending on the products, it can be integer or continuous. Integer if the products are discrete. For instance, you would like to deliver car, bus, table, or for example like bag or chair. But it can also be continuous. For instance, you would like to deliver gas or liquid like water, like alcohol or diesel oil, or maybe any other oils that is can be delivered in bulk. We have here four constraints. The first constraint limit the supply at plant I, because here we have capacity limit. In Nebraska we have 300 maximum. Colorado we have also 300, the maximum capacity to deliver. And therefore we have XIG, that X represent to the amount of delivery, the amount of supply from supplier I to transit point J. That's why it's called sigma J, because one supplier I can deliver to several destination of J, but the destination, the delivery or the from I to J cannot exceed the capacity of supplier I. And the second constraint, to satisfy the demand at final destination K. Here we have xjk, sigma j, equal to demand at final destination K. Why this sigma j? Because we allow the delivery to satisfy demand K by combining more than one transit point. Here, for instance, in order to satisfy demand at Chicago, you could combine supply from Kansas and Omaha. It is not a big problem and even not a problem at all. The main thing is that the demand at Chicago or St. Louis or Cincinnati are satisfied 100%. And there is no product are retained at transshipment points. Why? Because we do not allow that product after the lead time completed still left in Kansas or Omaha or Des Moines because there is no sufficient capacity. It is not allowed. So all product from Nebraska and Colorado must be 100% submitted to Chicago, St. Louis, and Cincinnati. And there is no way to dissatisfy these three final products points. And as usual, that all shipped products uh, do not allow negative value. So it is not possible, for instance, the number of shipped product is negative. It should be positive or at least zero. That's why there is a requirement higher than or equal to zero. And the objective function is to to minimize the total cost of delivery from Nebraska to and Colorado to Chicago, St. Louis, and Cincinnati. So whichever path or route taken by the supply chain, the goal is to minimize the total cost and to satisfy the demands at these three demand points. Okay, so now we can start our okay, now we have the same blank screen of our GAMS IDE. I think you still remember what we should first do in this blank. We should do in this flag first this blank screen. We have to put what is sets included in this modeling. We have here in this I, J, and K. So let's write this way. I is the supplier. What is the name of the supplier? Nebraska and Colorado. We have J here. It is the transshipment point. Okay. We have Kansas, Omaha, and Des Moines. Kansas, okay. We have K, it is a final destination. Sorry, I think we have to reverse sequence the Nebraska and Colorado. Okay, we have final destination here, Chicago, St. Louis, and Cincinnati. And do not forget to put semicolon. Okay. Uh, After defining the sets, we have to continue by providing the data here. we have AI supply of commodity at of source I and BK demand and CIJ CGK. Okay, let's start by building the table for. Okay, we have table. Okay, before continuing to this table preparation, we have to keep in mind that we have now more than one stage of supply chain. So it is much more easier to process the supply chain or to model the supply chain by building another index. We call it M, and therefore we have to put here alias. It is n comma mm and semicolon, and we have to put here I comma n, g comma n, and yeah, k comma n. Okay, and because we have n here, therefore we need to put here n set. It is called global set, where it takes values from 1 till 8. Sorry, 8. What's 8? Okay, yes. I think yeah, I think this is the right way to. Please keep in mind because we have named the nodes in our supply chain here by using city names. Therefore, we could put here not number but the city names. Here Kansas, okay, and Chicago, yes, that will be great. All right, all right, yes. Now we can develop our table. We have two kinds of uh, variables, xij and xjk, and also cost, it's cij and cjk. And now we have to compose the cij or cjk using the same way as we compose table in assignment problem. Okay, now I have composed the table that represent the travel cost from from uh, nodes n to node nm. Here n and nm represent the nodes I, J, or K. So it is some kind like we try to generalize the set I, J, and K so that it can be represented by set M here using alias. So n comma nn can be from I to J, can be J to K, or from K to I if there is a reverse flow, and even from J to I also. So it is make our model to be flexible. For instance, at future, if we have like reverse logistic modeling, and these are the table that we need to compose. For instance, here from Nebraska to Kansas, we have 16 US dollar per passenger or per unit. Okay, let's check. Nebraska to Kansas, yes, 16 exactly, and Colorado to Omaha, it is 14. Let's check it. Omaha to, sorry, Colorado to Colorado to Omaha. Yeah. Colorado to Omaha. Oh, where's Omaha? Oh, no, no Omaha. Oh, wait a second. Kansas. Oh, sorry, it should be in Omaha, not Nebraska. Yes. No. Okay, now everything is correct. And so how to read this table is that, for instance, here from this column to this row, for example, Kansas to Chicago, it takes 6 US dollar per unit. Kansas to Chicago. Let's check. Kansas, where is Kansas? Kansas to Chicago. Yes, exactly. It's 6. So uh, Cincinnati to Colorado, because there is no flows from Cincinnati to Colorado. That's why we set it as 0 here. Okay, let's see. Cincinnati to Chicago. Yeah, there is no flow. We can set as a 0. Anyhow, you can set anything, not only 0. If you want to put a very big number, for instance, like 100 or 1000 here instead of 0 is fine. This is not a big problem, because in optimization model it will be optimized accordingly, so that there is no any difference of result between setting the number to 0 or 1000 or even 100. So any number you can put, but this number, for example 16, 10, 12, you have to uh, put according to the problem here. Otherwise, the result will be different. And we have also capacity of our supplier here, n, 1, and 1 is equal to here I. It is 1, 2, 3, 4, 5, 6, 7, and 8. We have 300, and also demand at destination M, because N here, N6. What is N6? 1, 2, 3, 4, 5, 6, Chicago. Chicago here, equal to 200. Let's check it is correct or not. Yes, exactly, 200. And now we have already composed our tabulation for travel costs and capacity and the demand. The next stage is to develop or to set about the variables of this optimization model. What are the variables? Here we have only one variable. Oh, sorry, two variables, xij and xjk. Because we have represent ijk as n, it is ijk included into global set n. Therefore, we can put here variables x and comma mm. That will be written by GAMS x, delivery x, from I to J, or I to K, or J to I, K to J, or even I to I. So it is some kind of like a generalization of the index. And after composing the variables, we have to define the equation. Here we have how many equations? Oh, sorry, this would be 1, 2, 3. We have 5, but we can eliminate non-negativity constraint here by putting by adding positive in front of variables. So this means that variable always be positive, and therefore we have only 1, 2, 3, and 4. Yeah, 4 equation. Equation 1, equation 2, equation 3, and equation 4. All right, and do not forget to end this equation definition by semicolon. And we are now working with equation. We have to we have to write the equation line by line. Okay, let's start with equation number 1. From this model, we have xij, yeah, sigma j equal to capacity of supplier I. Then we can write here equation 1 because here the summation is j, therefore we have to put here I double dot and xij, therefore we have the summation of j, summation of j, then x I comma j xi comma j equal to capacity of I equal to capacity of I, and then semicolon. And next we have to compose the next constraint number 2. What we have here, xjk equal to demand k. Okay, okay, now we have equation number 2. Sorry, not this one, yeah, xjk, because the sigma j, then we have to put here k. Reason for putting I instead of j here in equation number 1, or k instead of j, is that because k already set here, we have already put j here, and it is not possible to put j here, otherwise it will be the number, I'm sorry, the index j here will be double, has doubling here, so it is not allowed in GAMS, because here I with equation 1I means equation 1 will calculate xij after summation all arc to j, sorry, all arc of j, that so we have xij, we have source I to destination j, but here j is here is j here from one I to several j. J already defined in this summation, because we need to sum up the number of delivery from single I to several j. Therefore, j has been defined in this equation, and therefore now we should should compute how much x from how much capacity or how much delivery from this supplier I to j should be available to meet the demand, and therefore we have here I. Similarly here we have xjk to satisfy demand at k. Okay, xjk to satisfy demand at k. So we have single j to satisfy several demand at k, and therefore we have here x a comma k is equal to demand of k and semicolon. Reason is that here we have sorry, we have here Yes, exactly. It is we have several G, several source J to satisfy demand at single K here. It is the reverse of previous equation. In previous equation, single supplier must satisfy several transshipment points. But in the second constraint, we have only a single K must be satisfied by several J or several transshipment point J. And therefore here we have a single K. So we need to compute how much delivery to a certain destination K so that uh, the demand will be satisfied. So here we have K because we have here some J already some uh, already have a summation here in this equation. So the left is only K. So for your easy understanding is that if you put here J, then you have to change this with other index, or otherwise it will be rejected by GAMS. And now we have another equation 3. Okay, now what equation to tell us about? Yeah, no product are retained at transshipment point. So xij it is should equal to xjk. Here we have uh, we can copy this. Okay, should be equal to this. All right. So let's look at this as this networks. So the number of delivery from 1 to 2 to these three transshipment point must be equal to delivery from these three transshipment point to the demand points. And therefore we have xij, all right, summation of total summation of I. Why this I? Because now we have to compute the total delivery from I. That's why this sum I, xij, it should be the total receiving from K. So here we have K. So the total delivery from here should be equal to the total receiving from to Chicago, St. Louis, and Cincinnati. All right. And because here we have I, we have K, so what is left? It is J. All right. Now you can predict, understand yourself, right? How to put I, K, J here. Whatever inside the summation here, the index, you should not put into this equation. Okay, so that's the rule of thumb of GAMS programming. Now we can uh, put here to make us not to be confused. Let's constraint. And write also here the objective function. Here we put equation number 4. We need to add variables here. This is equal to z. It's free variable because the objective function, and z is equal to sum of, because we need to calculate the whole cost of the supply chains, then we have to put all is here, I to j, and then xij, and plus sum j comma k, and this is c, and this is k. Okay, and semicolon. And what else? We need to uh, compile the models by naming the models here. Uh, transit trans transshipment. Yes. And then because now we have only four equation, it is better to write like this way. Otherwise, there is another easy. For example, if you have many equation, instead of writing this equation one by one, we can put all here, and we need to put solve and shipment using, because here we don't have integer variable as linear programming. The goal is to minimizing z. All right, now we have completed our model, and the left task is that we need to just run it. Wow, we have so many error here. What is the error? Oh yeah, we have double Nebraska, and therefore we have to change it a little bit. This one, Omaha, and yeah, here we have Omaha, and yes, okay. So we have to change also this one, Nebraska and Colorado. 678 at Chicago, St. Louis, and yeah, this one is better to copy. All right, so okay, let's hope it run perfectly. Well, yeah, now finally we can solve the problem. Okay, let's see what happened with the result. Nebraska to Nebraska 300, yes, it to itself, and Nebraska to Chicago 200, Nebraska to St. Louis 100, Nebraska to Cincinnati 300, Colorado to, okay, let's check this Nebraska to St. Louis, Nebraska, Chicago, St. Louis, Colorado, Nebraska, Colorado, Nebraska. Oh yeah, oh, there is something wrong here. Okay, okay, now we can start this model, and let's see whether we have composed the right modeling, and just press this one. Yeah, we have 1200, and here we have Nebraska 300 and Chicago. I think this is not the right solution at this time, because Nebraska would not deliver to itself, right? Nebraska to Chicago, it's not allowed because from here, Nebraska to Chicago, there is no direct flight or direct routing. We have to go maybe from Nebraska to Kansas or Omaha on the one before going through Chicago. And we have to learn why we have this kind of solution. First, I just realized that we need to tell the software or the model that there is some rules that is not allowed directly to deliver products from Nebraska to Chicago, for instance. And therefore, we have another tabulation here. We just copy this table and let's make it table A here. And whenever you have number here other than 0, you should put 1. Means it is allowed to deliver uh, product to this destination. Similarly, we can just copy here, put it here, this, and here we have 0, 0, yes, 1, this 1, and also this is 1. We can just copy this line and paste to this line also. So table A will tell the model that delivery from Nebraska to Nebraska is 0, means it is not allowed to deliver from Nebraska to Nebraska, even to Colorado, or directly to Chicago or St. Louis. And if the delivery from Colorado to Kansas, it is allowed because it has number 1 here. I think we should make this tabulation with structure, otherwise it would not be read by GAMS software. Again, because now we have table A, we have to include this table A in our constraint. Here we have sum J if, and we would like to introduce another symbol here using dollar. Dollar means if, and then A I, J, it is equal to 1, and Xij satisfy quality. And similarly, we also need to put here this condition A, but it is not Ij, but J, K. And here we have also if Ij, Ai equal to 1, but here we have if J, K equal to 1. I hope this will be sufficient to tell the model that there is no way to deliver from supplier to another supplier or supplier directly to final destination. And let's start to run the model once more. Yes, now we have the solution and check whether it is feasible or not. Yeah, now we have Nebraska to Kansas, Colorado to Kansas, Kansas to all 3 destinations. And the topology of this configuration has been changed by eliminating Omaha and the small ones. So we have only this path to this 3. So we can delete Omaha and this one because it's infeasible to deliver products from Nebraska to Chicago to Omaha, or even to St. Louis from Omaha, and Cincinnati from Omaha. And if, same case for these ones. So using these GAMS, we have already make the optimal solution for supply chain configuration of transshipment problem. What important result that we can extract from this model? Here we have Ciplex, IBM iLog Ciplex means this problem solved by using IBM iLog Ciplex solver, but you can choose whichever whatever solver do you prefer. But in this case, we are using Ciplex, and the optimal solution in 1,200 means the total cost of delivery is about 1,200. And yeah, we have equation. We have solved equation here. So this is actually the result for its constraint available. But at this stage, you need to understand only this result. How much to deliver from Nebraska to Kansas, go to Kansas, because it will represent our new topology of our supply chain. And what else we have? Yes, the number of iteration. I don't know how many iteration here we have. Maybe millions iteration. Oh, sorry, this is the limit, right? But actually we have 1,000 iterations, and it is optimal. The optimal, and how much for the, is there any information about the gaps? Gaps. There is no. Yeah. This model statistics tells us that we have 16 variables, 16 single variables. We have 4 equation, blocks of equation. We have 8 single equation, and we will discuss more about this model statistic, and this model has been solved by Ciplex within 0.062 seconds, and this is important actually for choosing whether Ciplex is the best solver for solving this problem. Of course, because we have very little size of problems, it is solved for about less than 1 second. But if our supply chains grow, sizes grow very huge, that contains maybe more than 100 stations or 100 destination or 100 suppliers, and the operation is not only about delivery but about production, and even some there is inventory control inside the model, then the execution time might cruise from less than 1 second to maybe hours. So we have to be concerned about this execution time. But for our problems, we have achieved optimality within 0.062 seconds. Okay, thank you for today. We will continue to the next video in stochastic programming that will be available within few days from now. Thank you.